This is the second part of our video on momentum and the more challenging problems. This is going to take a look at just two different types of problems, and pretty much what we're looking at here is we are going to integrate momentum with other concepts. Specifically, these two are going to use energy, but not every problem uses energy. So think outside the box, make sure you're keeping in mind all the things that we've done in the past and see how those can apply to this situation. So let's see, we have a 2 kilogram block is sliding on a smooth tabletop, so we know that this here is 2 kilograms. It's
I love
moving to the
physics.
left. We're going to say that this velocity to the left is a negative value. It says that it has a total inelastic collision with a 3 kilogram block. So we know this is 3 kilograms. And this inelastic collision tells us that energy is not conserved. Right? With inelastic collisions, energy is not conserved. And this is a very important thing when you're dealing with momentum and energy. So let's see, both blocks are now moving together and hit the spring and compress it. Once the blocks come to rest, the spring restores itself and launches the blocks. They slide off the right side of the table. The spring constant is 775 newtons per meter, so 775 newtons per meter is our spring constant. A, find the velocity of the two blocks after the collision, and B, the distance the spring is compressed. Let's do those and we'll come back. So we know that this is an inelastic collision, right? And A wants to know the velocity of the two blocks after the collision. So we have block 1 moving at its own velocity. We have block 2 essentially sitting still, so that's going to be 0. And afterwards, because it's an inelastic collision, we know that both the block 1 and block 2 are now moving together at the same velocity. As I said in the diagram, that block 1 is moving to the left, so we're going to call left negative. So it's moving at -10. Block 2 is not moving, so it has no momentum. And we're looking for how fast both block 1, which is 2 kilograms, and block 2, which is 3 kilograms, how fast those blocks are moving. And they are going to kind of slow down that 10 meters per second, and it's going to be moving still to the left, but at 4 meters per second, because both masses are now moving together. Let's see, part B. Right, we're looking for the distance that the spring is compressed. Well, we know that both of those blocks have energy. Oops, that should be a V. Right, both of those blocks have energy, and when they hit the spring, all that energy is going to be stored in the spring because those blocks, it says, are going to come to a rest. So 1/2, right, the mass of both blocks moving together is 5. We know that together they're moving at 4 meters per second. Remember, energy is a scalar quantity, so we drop the negative in the -4 meters per second. And all of the energy is going to be stored in the spring. It gave us a spring constant of 775, and we're looking for what X is. Punching that in your calculator, you get X is equal to 0.32 meters. And really, if you're being thorough, we really should say that this is a negative value. I know I kind of drew it down there pretty far, but it should be a negative 0.32 meters because it's being compressed to the left, not to the right. Moving on to question C. Question C says the velocity of the blocks after they leave the spring. Well, it says, let's see, where is it? Because it's the spring, right, and it doesn't talk about any sort of work being done by the spring or any sort of energy lost and so on. Whoa, what just happened? So that's how you get this answer for C here, is that it's saying it's going to move at the same speed because no energy is lost in that deforming the spring and rebounding. So now it's moving at 4 meters per second to the right, or positive 4 meters per second. Part D, the distance the block travels before they hit the deck after they leave the tabletop. Well, this basically becomes a free fall problem now. So it's hard to navigate. Where are we? Okay, so we're going to get both of these blocks, right, are going to come together, compress the spring. They're going to move back on this table, and at this point, both blocks together are going to fall off and become a projectile. And we want to know the distance that the blocks travel before they hit the deck. So essentially, we want to know what is this distance that they're going to travel. So let's take a look at how to do that. Our first step is going to be figure out, typical projectile problem, how long is the object in the air? So we know that it is going to fall oops, that should be a y. So we know that when it comes off of this horizontal table, the initial y velocity is 0. It gives us the height of the table in the picture, so it's going to fall 1.2 meters, so that's why it's a negative change in y. It's in free fall, so the acceleration of gravity is 10, and that allows us to find the time, which is 0.49 seconds. So the blocks are going to be in the air for 0.49 seconds. We are looking for that range, or how far it travels. We know that the speed it's traveling in the x direction was that 4 meters per second, and we now know the time it has to travel at 4 meters per second. So we have our Vx is 4, our 0.49, which gives us basically half of that, right? So our delta x is going to be roughly 2 meters is how far it's going to travel before it hits the ground. And our last part, part E, the kinetic energy of the blocks at the bottom just before they hit must equal the potential energy at the top of the table plus the kinetic energy of the blocks had before they begin to fall. Oop, sorry, what are we looking for? E. Oh, we're looking for the kinetic energy of the blocks just before they hit the deck. So essentially what that was saying there in part E, that description is saying that when the blocks are on the table, they're moving at 4 meters per second, so they have kinetic energy. They are 1.2 meters off the ground, so they are storing gravitational potential energy. And right before they hit the ground, both blocks are going to be moving, but essentially have no more gravitational energy because they're about to hit the ground. So keep in mind that the mass is 5 here, right? And we could have canceled it out if we wanted to. On the table, they're moving at 4 horizontally. Energy is a scalar quantity, so we don't care about direction. So we don't have to worry about separating anything to x and y's and all that kind of stuff. Let's see, both blocks are on the table, and they're at a height of 1.2 meters. And that allows us to figure out how fast they're moving right before they hit the ground. And is that what we're looking for? Sorry, it's asking us, oh, we just want the kinetic energy right before they hit the ground. So that's even easier, right? 4 squared is 16. Half of 16 is 8. 8 times 5 is 40. And then 5 times 10 times 1.2 gives us 60, which means there is 100 joules of kinetic energy right before it hits the ground. If we did go through and solve for that velocity, remember that it's going like this, right? So at this point, it's moving at a velocity in that direction right before it hits the ground. It would give us this diagonal velocity. That wouldn't be the velocity in the x, it wouldn't be the velocity in the y, it would be the overall velocity. So let's move to the last problem, and this one will not take as long, I promise. The ballistic pendulum is a device used to measure the speed of a fast-moving projectile, such as a bullet. The bullet is fired into a large block of wood suspended from some light wires. The bullet is stopped by the block, and the entire system swings up to a height of h. So this bullet right here is going to lodge itself into the block of wood. It's going to then travel up here, and at that point, when it gets to the maximum height, it's going to stop at that maximum height.
Look, it's a stapler.
Let's see. So if is possible, that should say it is possible to obtain the initial speed of the bullet by measuring h and the two masses. As an example of the technique, assume that the mass of the bullet is 50 grams. Be careful with the units there. The mass of the pendulum is 1 kilogram. That's in the proper units for mass. And the height is 5 centimeters, which means it is 0.05 meters as far as the height that goes, right? So we know that this height is 0.05 meters. Find the speed of the bullet. So we want to know, what is this speed? The key here, again, at this location, when this is an inelastic collision, we know that energy, right, is, oops, that should be a T, is not conserved. So let's work through it. Our first step is going to be figure out how fast the block is going after the bullet is lodged inside of it. So I'm going to erase some of this to try to clear this up. Okay, so in this scenario, when the bullet is in the block, how fast is it going at that point? And we can use energy to figure that out, because at this point, right, it's moving when that bullet becomes lodged in it. So we know that, let's see here, we have 1 plus 2 nRV initial squared, right? That our bullet and block are both together, and they're going to have kinetic energy, and they're going to raise up to this point and stop. And so at that point, the only type of energy they have is gravitational potential energy. And you don't have to separate out the masses like that. If you know to put them together, that's fine. So we have our 1/2 1.005, that's the block of wood and the bullet, and we're looking for this velocity, and we know that when it gets to its highest point, our 1.005 kilogram object has gravitational potential energy, and remember that it has a height of 5 centimeters or 0.05 meters. So what we find is that the initial velocity of the bullet and block together is 1 meter per second. Now the mistake that people will make is they'll act like energy is conserved. Remember, it's inelastic, so energy is not conserved. We now know that we have the block and bullet moving at 1 meter per second after the collision. Well, before the collision, we had two objects that were independent of each other. So, right, after the collision, we know that both the block of wood and the bullet are moving at 1 meters per second. We're looking for how fast was that 0.005 kilogram bullet moving before it hit the wood, and of course the wood wasn't moving at all initially, so it had no momentum. So now, using conservation of momentum, we can find that the bullet was actually going 201 meters per second before it struck the wood. So hopefully you see the key here is keep in mind that we have conservation of energy and conservation of momentum, and when energy is not conserved is in an inelastic collision. So be very, very careful of that aspect. Otherwise, make sure you're using all your old equations that have to do with acceleration and free fall and projectiles and all of those, because you're going to see those show up in the homework also.